Hey guys, how's it going? So nice to finally meet you all in person and get through our first learning target together. So we're going to work on our second learning target in quarter 4, which is thermodynamics. And so we have a few big ideas and learning objectives to talk about today. So our first big idea is heat is a transfer of thermal energy that occurs spontaneously from a warmer object to a cooler object. And we have 3 of our learning objectives we're going to talk about in this first section. So energy is not a substance, it doesn't have mass, and it doesn't have a volume. It's pretty tough to conceptualize what energy is, but it changes in matter involve changes in energy. So anytime you have matter changing form, whether it's from a solid, liquid, or gas, or changing from carbon dioxide to carbon monoxide or water or anything like that, you are involving a change in energy. Energy is identified as a measure of the ability to cause change to occur, and its unit is the joule, which we represent with a capital J. We see energy as light, we hear it as sound, and we feel it as heat, and energy is everywhere, and we would be lost without it. Here are kind of the forms of energy in a little schematic and how we can kind of think about them. There's really 2 main types, kinetic and potential. Kinetic energy being that energy of motion, potential energy being that stored energy. Kinetic energy then can be broken down into thermal energy, mechanical, electrical, magnetic, and you can see what each of those are there below. Potential energy then can be chemical energy. So like I have an apple down here. This apple has stored chemical energy in it that my body then can convert into mechanical energy for me to walk. So this stored chemical energy, gasoline in your car is another example of that. Elastic energy, nuclear energy used in nuclear physics and power plants, and gravitational energy. So kind of like water, for example, flowing out of your faucet flows due to gravitational energy causing it to flow. Oh, there's also sound energy and then light energy. So lots of different forms that energy can take that again are essential and we use every day of our lives. So when we talk then about heat, heat is the transfer of energy between 2 substances due to temperature differences. So the heat is that transfer of energy. And so when we talk about thermodynamics in this class, we're talking about 2 things. We're going to talk about the system and we're going to talk about the surroundings. The system is anything that you're focusing on. So it's the chemical reaction or process you're focusing on. And the surroundings are everything outside of the system. So in this case, the water and the ice are the system, and the surroundings would be the cup, the air. If I had a spoon mixing in there, that would also be the surroundings. It's not a part of the chemical system. And so when we talk about heat relationships and energy, it's important to understand the difference between system and surroundings. So heat transfer, we can also transfer that heat. We can transfer that heat in a couple different ways. And the transfer or the direction of heat is always from hot to cold. Heat is always transferred from the warmer, hotter object or substance to the colder one. So convection is one type of heat transfer, and that is when heat is transferred through a fluid caused by molecular motion. So convection. If you have a convection oven, it blows the air around the oven to keep it more evenly distributed, where most ovens at your house are just going to heat from the bottom and hope that the heat rises to top and spread through, but it's not going to have that convection current that's going to cause the oven to cook a little bit faster. Conduction, this is how we cook most of our food. We conduct the heat. It's a transfer of heat or electric current from one substance to another by direct contact. So you put your pot on the stove and it conducts the heat through it. Radiation is another one, and that is when energy is radiated or transmitted in the form of waves or rays. So this example here, the fire is radiating heat towards the pot. The metal of the pot is conducting its heat to the liquid in the water on the edges of where it's touching the pot. Then the water molecules, as they bump in, get excited to each other, are convecting that heat transfer to each other. The next thing we're going to talk about is thermal equilibrium. And so again, we're talking about heat, we're talking about temperature, and we're talking about the fact that heat goes from hot to cold. So when 2 objects are in contact with each other, they reach the same temperature, they are at thermal equilibrium. If I put some cold water and some hot water and I mix it together, they are going to reach an equal point. It's not going to be exactly in the middle depending on the type of solution. It's going to vary a little bit, and also depends on volume. So in this example, we have a 0-degree substance and 100-degree substance. They look to be the same amount by the size of the square. If I mix them together, thermal equilibrium in theory should be roughly that 50-degree mark right in the middle, because I'm doubling the amount I have, but having a high and a low temperature there. So what happens when you open a window on a cold day? According to our thermal equilibrium and our convection, our heat transfer, what is going to happen when I open that window on a cold day? Is heat going to go which direction? Remember, things always from hot to cold. If it's cold outside, hopefully it's warmer inside your house, and air is going to rush out your window into the surroundings, the system being your house, the surroundings then being the outside, and the heat's going to rush outside, and it's going to start to feel colder in your house because that hot air is leaving your house. Which leads us to these two big terms that often students have a hard time with deciding which is which, and hopefully by the end of this class you'll have a little bit better understanding. Exo and endothermic. The prefix exo literally means exit, and endo literally means in. And so one way to look at this and think about it is with these images. In an exothermic reaction, heat is released from the system to the surroundings. This will feel hot to us because we are the surroundings. The system is losing heat to the surroundings. In an exothermic reaction, this is going to feel cold to us because the system is taking heat from the surroundings and going into the system. This is going to feel cold, where exothermic is going to feel warm for us because that heat is coming from the system to the surroundings. In this case, the system is taking in heat from the surroundings. And we can represent that in a couple different ways with the drawings I just showed you, or with these potential energy diagrams. You saw these in your virtual lab, and for an exothermic potential energy diagram, energy again is being released from the system to the surroundings. So our energy is being released to those surroundings. In an endothermic reaction, energy is being absorbed. So if we look at potential energy on our y-axis here, it is increasing. So if my reactants start with a higher energy and they release it, they're going to have a lower potential energy after the reaction happens. In an endothermic reaction, the reactants are taking energy from those surroundings. Energy is being absorbed. They are going to have higher potential energy than the surroundings. Activation energy is the energy required for the reaction to start. And so think about this like kicking a soccer ball over a hill. If you kick it only a little bit, it's not going to go all the way over the hill. You have to overcome all of the potential or the energy to get to the top of the hill before the soccer ball will roll back down the other side. So this potential or this activation energy is the energy required for the reaction to even start. And so in this exothermic process, we can see it's a lower activation energy. It's more likely to occur without a lot of external help. In an endothermic reaction, we usually have a higher activation energy, and it requires a lot more energy to begin the reaction. So let's take a look here. I have a reaction diagram here, a potential energy diagram. Is this an endo or an exothermic diagram? Can we tell our reactants are higher in energy than our products, meaning what? Energy must have been released, and that is an exothermic reaction. Energy is being released to the surroundings, and the products have less energy than the reactants. So in delta H is that change between the reactants and products. And you read it like you would like a graph, right? So we're going from a higher potential energy to a lower potential energy. That means we have a negative delta H. And this is where students, I think, really struggle. When I have an exothermic reaction, I am going to have a negative delta H. And sometimes that's confusing because you think exo, like positive, warm, but that's not the case. Our delta H, or our change in energy, our enthalpy is what it's called, is going to be negative in this case. Where is that heat going? Remember, it's going to the surroundings. It's going from the system, whatever that reaction that's happening, to the surroundings, okay? Again, exothermic in this case because our delta H is going to be negative. We're going from a higher energy reactant to a lower energy product. Where if we looked at our endothermic process, this would be a positive delta H or a positive enthalpy because energy is being absorbed by the system. So delta H is defined by the system, not the surroundings. So let's do another little practice question here. Make sure you pause the video before I go over the answers so that you can try it on your own. Use this diagram to answer the following questions. The enthalpy of the reactants. Enthalpy is just the fancy word for the energy or the heat of the reactants. The enthalpy of the products. The threshold energy. The activation energy. And the change in enthalpy or that delta H value. So again, pause the video and try to see if you can identify those answers. And then here they are. So our enthalpy of the reactants is at 20 kilojoules per mole. The enthalpy of our products is at 50 kilojoules per mole. Our threshold energy is going to be that sum of the energy at the top of our reaction curve, and that is 100 kilojoules. Our activation energy is going to be the difference from the threshold to your products here, so that is going to be, it's going to be the total from the reactants to the top here. And then your activation energy is going to be, again, from your reactants to your products. And then your change in enthalpy is going to be that delta H. It's going to be the change from the reactants to the products. In this case, we have a positive delta H, so this leads us to believe, and from the diagram, that it is an endothermic reaction. The system took in energy from the surroundings and gained energy. So we have a positive enthalpy or delta H here representing an endothermic reaction. Let's pause.